Right. So I just want to show you a little bit of what we have planned to cover during this week on the MR notebooks. So I will also try to help you on the MR side with the notebooks. And the second MR expert we have here is David Atkins from UCL. And he will also be there then to also on the Wednesday sessions to discuss some problems. As mentioned before, we have SIRF, and then SIRF is not really an image reconstruction package in itself, but it links to other ones. So there, for the MR world, there are several. There's BART, for example, it's from Berkeley. There's also Gadgetron, and we decided to link SIRF with Gadgetron to have it as our MR reconstruction engine. You've already seen that you have to start a server, but we'll get back to that also a little bit later. Then you have also the other parts, which we'll cover in the next talks after me, about the PAD and the CIL functionality. Now, in MRI, as I've shown you before, right, we have an MRI scanner. We put an object inside with the acquisition model. We get our acquisition data. We call it raw data, or measured data, or case-based data. Then we do some image reconstruction. We get our image out of there. Now, I don't want to go into too much details about the physics behind there. Just show you a few examples. As already mentioned, you find quite a lot of material on the HackMD side. So there are lectures also by me, but also by other people on the kind of the physics behind there for at least image reconstruction purposes. So if you want to know more about them, then please have a look there. And so I would just try to be very brief here today. So in MRI, it's sense for magnetic resonance imaging. And the magnetic basically means that we have this whole machine here is basically one strong magnet. So we put an object like a patient inside, and because of the magnetic field interacts with the nuclear spins of our hydrogen molecules, we get some measurable magnetization, which we call M here. Now this is an equilibrium state, so we don't get any information. So what we need to do in order to probe that system is we apply another magnetic field. And this kind of deviates this magnetization from its equilibrium, and then we watch how it goes back to the equilibrium. This is the mass signal which we can acquire. Now, this signal basically the sum of all the hydrogen nuclei which we have probed. And so in order to do imaging, we need some additional gradients. So we need to locally vary our magnetic field, and then we can encode our data into an image. So again, here we have this part here, and then we use our imaging gradient. And this case here, we have to somehow sample this case space. So we have to acquire discrete points of this of our case space. And this example here shows some Cartesian sampling. So we have this kind of parallel lines here, which we cover our case space. And based on that, then because it is a regular Cartesian sampling, and ideally we can actually add just a fast Fourier transform and get our image out of there. Of course, it's not so simple in itself because there's a lot of things you have to take care of. But luckily enough, we don't have to do that, but Gadgetron does all of that for us. And so basically what we just have to do is we have to get a data from our scanner. Based on a lot of information in the data, we can set up our acquisition model. And then most of the things are taken care of by Gadgetron or the SIRF wrappers around that, such that we can do a very simple reconstruction. And also for the remainder of the course, we will stick to Cartesian sampling. But Gadgetron specifically, but also SIRF now has the capabilities to do non-Cartesian sampling, but that would be too far for this training school here. So we'll stick with Cartesian sampling for all the example notebooks we are providing here. Now, maybe a little bit on the raw data. So as mentioned a couple of times, the main aim of SIRF is that we can actually reconstruct real data. So we don't just want to simulate some data and then do some very basic reconstruction as for teaching purposes, but we want to do the teaching based on real data. And so with SIRF, we decided to have also an open source data format, which we support for the MR side. This is called ISMRD. So ISMRM is the largest society for magnetic resonance in medicine. And a couple of years ago, they came together and decided to come up with one data format, supported to a certain degree, at least, by most of the big vendors, such that there's one format which we can use for image reconstruction. Each vendor, of course, has their own data formats, and luckily enough, there are some tools which allows you to transform from one data format to the other. So you find that here under github.com and ISOMRD, and here you have these different tools. So there's Siemens to ISOMRD, there's Bruker to ISOMRD, and Philips to ISOMRD. So basically you can give it a raw data file and sometimes some other information, and then it translates it into this ISOMRD format. And this you can then put basically into our SIRF reconstruction and reconstruct it. That's a little bit of a caveat here. So Siemens is very well supported. So you can basically transform, to my knowledge, any Siemens raw data file to this ISOMRD, and it will do a sensible job, and you will be able to reconstruct that, not necessarily with SIRF, but at least in principle. The other vendors are less so supported. So there are some support for some very basic raw data files, but it's still a little bit limited. Again, it's a community effort, so the more effort people put into that in order to make that possible, the more people will benefit also from this. So mainly we have been focusing so far on Siemens data because, also as mentioned before, originally SIRF was designed for simultaneous PET-MR imaging. This was then based around the simultaneous PET-MR scanner from Siemens. You can also find more information on that on our website. So there's on the GitHub site, there's also a wiki. Please have a look through there. There's also one entry on MR raw data, and there you can also find some explanation. You also find explanation how to use that. So of course you won't need to use it for the exercises here because everything will be already in this ISOMRD raw data format. But say you have your own data and you just want to give it a try, and have a look there, have a look how you can translate that. So this functionality is part of or can be installed with SIRF. And so you can directly use that in order to transform your raw data file to ISOMRD, and then in principle you can put it into our SIRF reconstruction examples. Even if you're struggling, then please also report that back to us. It's also helpful for us to know what works and what doesn't work yet with SIRF. Now coming back to our exercises, as mentioned before, you have this folder here on SIRF exercises, and then there's notebooks, and then the MR. And in the first week, we're going to cover these three notebooks here. Just as a small repeat again, but I'm sure even I most of the time forget about that. You need this terminal here in order to start the Gadgetron server. So this is a client-based method, so which means that there's a client running in the background waiting for data, and this SIRF is sending this data, but you still have to start the client. The main reason for this is that this was designed to be actually able to send data to a reconstruction client running somewhere else from the scanner, so that you can directly reconstruct data acquired with the scanner, send it to a Gadgetron client, and then it's sent back to the MR scanner to have a basically full loop and have the reconstructed image data back on the MR scanner. This is also shown here again, so that's what also been shown before, that how you can start this Gadgetron server, and once you hit enter, you will get this basically terminal output, and then you know everything is running. Also shown before, but again, to emphasize again, what can happen if you do that is that you open your terminal and you type in your Gadgetron, but now it's not working. You actually get this error message, and so here it's already running. But you can either then go here to the running and see which terminals are running, and then you can select one of those, or you can use the shutdown to shut them all down and restart your terminal. So now a little bit more on the notebooks. So there's the one, I won't show you the notebooks because there's a lot more information in the notebook. So it's not just code, but there's a lot of more explanation. I think it makes more sense for you to go through that by yourself. That's how they are designed. But I just want to give you a little bit of an overview of what they roughly cover and what you should know before and after the notebook. So the easiest one here is it's fully sampled. And here we'll go through all the basics again. So again, making sure that you have the training data. If you haven't downloaded how Edo showed it before, but there's also another bash in there how you can download it again or extract it again. There's also, again, how to connect to the Gadgetron to make sure that this client is running. And there's also information about Python programming and in general that do the Python programming into the Jupyter notebooks. It's a lot of basics, which is actually not MR specific, but just to get you into interaction with these notebooks. Then we look at more MR specific things. So first, what is the layout of the raw data? So looking more into this ISMRD data format to better understand that. And then also how to do your first image reconstruction using the Gadgetron. So sending data to the Gadgetron client and then getting your image back and displaying that. The main thing you're going to interact here is the so-called acquisition data object. So this is the raw data or case-based data from the created from an MR raw data file. And this acquisition data is basically just a long list of acquisition objects. Each acquisition object is just one line of your case base. And of course, in principle, you have to know kind of at which position they have been acquired and how you can put them all together into a case base in order to do your password transfer. But luckily enough, you don't really have to worry about that because Gadgetron takes care of all of that. And here you will also then see a little bit what you can do with that. One thing which I want to point out here, one really important function here is the help command. So if you type help acquisition data, for example, you get a lot of information of what this object actually is and what it can do. So I strongly recommend that you do that repeatedly to see just all the options there are. We try to show you some things it can do, but there's really a vast number of different functions and parameters there are. And with this, you can probe that and see what's going on there. Now, the second notebook is a case-based filter notebook. And here again, we will look into getting information about the acquired data, but then more importantly, how can we interact and even modify the acquired data? I draw this very simple picture here. So the idea is, how can I interact from NumPy to SIRF? So Chris told you before, right, that SIRF in principle is a wrapper around lots of different functions, such as Gadgetron. But Gadgetron, for example, is in C++, is written in C++. So doing some simple testing there is a little bit difficult. You have to compile that and you have to set it up and so on. So it's much more convenient to actually do the programming Python for some rapid prototyping. And this is kind of what should highlight this functionality in SIRF here, that on the one hand, with a very powerful reconstruction engine, which is really fast because it's implemented in C++, but on the other hand, we can directly interact with that using NumPy or any other Python functionality. So here you will see how you can just obtain data from a SIRF object, which underlying is a C++ object, into a NumPy array. You can modify that very easily, and then you can put it back into your reconstruction pipeline. Yeah. And that's a very powerful concept, which sounds quite trivial here, but it means you have this really ease of use of the software while still being able to reconstruct very large data sets in a reasonable reconstruction time. And the last notebook for this week would be the call combination one. So here you will learn what are core sensitivity maps and why do I need them? How can I calculate them from the data which I've acquired? And how to actually combine this data from acquired with different receiver arrays. I don't know how familiar you are with MRI, but this is an MRI scanner, which I said is basically a big magnet. We use that to basically create a signal, but a signal reception is done with the so-called receiver arrays. So here you can see head coils, here's a cardiac coil, and here you can see basically a full body setup. So this one creates the signal, and with these ones we receive them. And in there you have lots of small arrays. So each one of these loops here is basically an antenna which can obtain the MR signal. But in the end, which means we don't get just one case space for one image, but we get one raw data, one acquisition data for each of these coil elements. And then in the end, we have to think of how we use that in the image reconstruction. Originally, this was done in order to prove the SNR, because it turns out having these local elements here is much better, gives you a much better SNR. But actually, later it turned out it's also very interesting for image reconstruction purposes, and we'll see more of that then in the second week. here's just an example. Here again, a slice through the brain. And these white bars here should symbolize the receiver array elements. And so each of them would produce its own case-based data. And if you reconstruct an image, you basically get 4 images of the same object, each looking at a slightly different part of the brain. The question is in this notebook, first of all, how do we reconstruct those, and how we can also combine those to an image which is then diagnostic. So because we don't want to show these 4 different images to a clinician, but actually would like to look at one single image which we actually acquired. And here again, we have this object, it's called coil sensitivity data, where we can put in some case-based data, and then we can calculate our coil sensitivity maps. And you can see you will see in this exercise then some of the parameters, some of the things you can do with this object then. So that brings me more or less already to the end. As I mentioned before, they are very verbose if you want. So there's a lot of text in there, but take your time, read through that, because we will then build up on that in the second week to these things which you have learned there in these notebooks. Again, on HackMD, you find some more materials, so proper lectures then on topics covered here. If you're interested in more details, then please refer to those. And if you're still then unclear about something, then please write them on the HackMD site if you have any questions. And we'll try to answer them then on the Wednesday session or on the Friday session. Before I finish, just something on a more specific, if we haven't really worked with that so far. In contrast to most other modalities, MR raw data, so the acquisition is actually complex, so it's not real valued. The image data is also complex, not real valued. And if you look at the SIRF image data object, even if it's 2D, you will always have these shapes. Just keep that in mind when you plot that data, but you will also see that in the exercises then. Okay, that brings me to the end. So are there any questions?
Some of questions in the Zoom chat, but I didn't see anything specifically to you immediately.
Just password stuff.
Password stuff, yes. Docker doesn't run.
Oh, there was a question about what's the relation between ISMRD format and Dicom, which was probably more.
Okay, yeah, so basically no relationship, in the sense that Dicom is a file format for image data and ISMRD is really for raw data.
Yeah, and the same will be true on the PET side. Different data format is used for the raw data than for the images on your scanner. And we need to cope with both.